Imagine shrinking down smaller and smaller until you reach the scale of a single human cell. A cell is incredibly small. So small that millions could fit on the head of a pin. And yet inside that tiny space is something remarkable. A long, delicate molecule that quietly carries the instructions for life. This molecule is called DNA. Every living organism on Earth uses DNA. Plants, animals, fungi, even microscopic bacteria. Inside your body, nearly every cell contains the same DNA. A complete molecular blueprint describing how that body grows, repairs itself, and functions. Tonight, we'll take a slow journey through this quiet molecule, exploring what DNA is, how it works, and how it connects every living thing on Earth. DNA stands for deoxyribonucleic acid. Despite the complicated name, its structure is surprisingly elegant. Imagine a ladder. Now gently twist that ladder into a spiral. This shape is known as the double helix. The sides of the ladder are made from repeating chemical units, and the rungs are formed by pairs of molecular bases. There are 4 of these bases: adenine, thymine, cytosine, and guanine. They pair together in a very specific way. Adenine with thymine, cytosine with guanine. This pairing system allows DNA to store information with remarkable stability. One of the most remarkable things about DNA is how universal it is. The same 4 chemical letters appear in nearly every organism on Earth. The same molecular code that builds a human cell also appears in bacteria, plants, and whales. Life, in all its diversity, shares a common molecular language. Inside each human cell lies an extraordinary amount of genetic information. If you stretched out all the DNA in a single cell, it would measure roughly 2 meters long. Yet it fits neatly inside a microscopic nucleus. Altogether, the human genome contains around 3 billion base pairs. Today, scientists can read DNA more easily than ever before. Entire genomes can now be sequenced in a matter of hours. This growing knowledge may help doctors treat diseases, understand human biology, and explore the deep history of life. Every day inside your body, billions of cells quietly divide. Skin cells replace older ones. Blood cells are renewed. Tissues slowly repair themselves. But before a cell can divide, it must do something extremely important. It must make a complete copy of its DNA. This process is known as DNA replication. At first, the double helix begins to gently unwind. The two strands slowly separate from each other. Some scientists describe this step as being similar to unzipping a zipper. Each half of the molecule becomes a template for building a new strand. Special proteins move along the DNA like tiny molecular machines. They read the exposed bases one by one. Whenever the enzyme encounters adenine, it adds thymine. When it encounters cytosine, it adds guanine. Gradually, two identical DNA molecules are formed. Each new molecule contains one original strand and one newly built strand. This elegant strategy helps maintain accuracy. If a mistake appears, the cell's repair systems often detect and correct it. In this quiet and constant way, the genetic instructions of life are copied again and again. Cell after cell. Generation after generation. Even though DNA replication is remarkably accurate, it is not completely perfect. Occasionally, a tiny change appears in the sequence of DNA. This change is known as a mutation. A mutation might involve a single base being replaced, or sometimes a small segment of DNA being inserted or removed. Many mutations have no noticeable effect at all. The cell continues functioning normally. Some mutations, however, can slightly change how a protein is built. Over very long periods of time, these small changes accumulate. And this gradual accumulation is one of the forces that drives evolution. When a mutation creates a useful advantage, it may help an organism survive or reproduce more successfully. Across thousands or millions of generations, these tiny variations shape the diversity of life. The wings of birds, the camouflage of insects, the remarkable adaptability of plants. All of these differences began as small changes in DNA. Quiet molecular edits slowly guiding the long story of life on Earth. DNA does not only describe the present. It also carries traces of the past. Every generation inherits DNA from the one before it. Parents pass their genetic instructions to their children. Over time, this creates an enormous biological record stretching backward through history. Scientists sometimes compare DNA to a kind of historical archive, written not in ink but in chemistry. By studying genetic similarities between species, researchers can trace how different organisms are related. Humans share much of their DNA with other animals, even with creatures that appear very different from us. This shared genetic heritage reveals that all life on Earth is connected through deep evolutionary history. In some cases, scientists can even study fragments of DNA from ancient fossils. This field is known as ancient DNA research. Through these fragile molecular clues, researchers have reconstructed genomes from extinct species, including our distant relatives, the Neanderthals. Each fragment of DNA acts like a small whisper from the past, helping us understand where life came from and how it slowly changed across millions of years. And even now, inside every cell of your body, that long spiral molecule continues its quiet work, carrying the story of life forward one generation at a time. If a phone can whisper your location with quiet confidence, it can feel a little like magic. But the secret is not magic. It is time, and a small chorus of satellites moving calmly overhead. Welcome to Curious Nights. Tonight's sleepy documentary is GPS Explained Gently. Time, satellites, and knowing where you are. Our setting is a night museum. The galleries are dim. Glass cases hold old compasses and quiet instruments. And above us, in a dark ceiling painted like a sky, tiny lights suggest steady orbits. This is gentle education, not advice. You do not need to remember anything. If you drift off, the museum will simply keep its calm. And we will keep moving slowly. We begin with the most surprising fact about GPS. It is, at its heart, a timekeeping system. Position comes later. First comes time. Imagine a sound in the museum. A soft click from a clock in a display case. If you knew exactly when the click happened, and exactly when you heard it, you could estimate how far away it was. Light works in a similar way, only much faster. A GPS satellite sends out a radio signal. That signal carries a timestamp. Your receiver, in a phone or a car, notes when the signal arrives. The difference between those two times is the travel time of the signal. And travel time becomes distance. This is why clocks matter so much. Radio signals move at the speed of light. So tiny time errors can become meaningful distance errors. A small drift in timing can look like you moved, even if you are still. To keep time steady, satellites carry extremely precise clocks. These are atomic clocks. They are not ticking because of gears. They are ticking because of consistent natural rhythms inside atoms. It is a quiet, disciplined kind of time. Your receiver does not usually have an atomic clock. It has something more ordinary. So the receiver assumes its own clock is a little imperfect. And it plans to solve for that imperfection. Later, we will see how it does that, with help from extra satellites. For now, just keep one calm image in mind. GPS is like listening for distant bells, noting when each bell rang, and using those differences in time to understand distance. Distance, repeated from several directions, becomes location. Now we look up. Not in a dramatic way, just gently, as if the museum ceiling has opened into a calm night sky. This is where the satellites live. GPS works because there are many satellites spread across the sky. They orbit high above Earth, high enough that they can see large portions of the planet at once, and arranged so that, from most places, several are in view at the same time. Each satellite continuously broadcasts a signal. The signal contains a timestamp, and it also contains information about the satellite itself. In simple terms, it says, "This is who I am, and this is where I should be." That "where I should be" part is crucial. Your receiver needs to know two things at once: how long the signal took to arrive, and where the signal came from. If you know the satellite's position and your distance from it, you can imagine a sphere around that satellite. You are somewhere on that sphere. With another satellite, you get another sphere. Where spheres overlap, the possible locations shrink. With enough satellites, the overlap becomes a specific point. This is the calm geometry underneath the system. There is also a gentle detail that often goes unnoticed. The satellites are moving. The receiver is moving too, sometimes. So the system is always solving a living puzzle, updated moment by moment. It does this quietly, in the background of your day. And GPS is not alone in the sky. There are other global navigation satellite systems, different constellations, with similar ideas. Many modern receivers can listen to more than one system. More satellites can mean a steadier solution, especially in tricky places. Now we step into the heart of the method: how a receiver turns signals into a position. We can take it one slow piece at a time. Start with one satellite. You measure your distance from it. That gives you a sphere of possible locations. You are somewhere on the surface of that sphere. Add a second satellite. Now you have a second sphere. The spheres intersect in a curve. Your possible locations shrink again. Add a third satellite. Now the intersection narrows further. In an idealized picture, you get one main location near Earth's surface. But there is a complication. Your receiver's clock is not perfectly aligned with the satellite clocks. This is why a fourth satellite is so important. With 4 satellites, the receiver can solve for 4 unknowns: latitude, longitude, altitude, and the receiver's clock offset. That clock offset is like a small correction, quietly applied. The distance measurements in GPS are often called pseudo-ranges. They are pseudo because they include small errors. Errors from the receiver clock, from the atmosphere, from the environment around you. But with enough signals, the receiver can still find a stable best fit. There is also the geometry of the sky. If satellites are spread out in different directions, the solution tends to be stronger. If they cluster in one area of the sky, the solution can be less certain. This is one reason location can feel better in an open field than between tall buildings. Now we come to the gentle imperfections. Not flaws, exactly. Just the real world, softly interfering with pure geometry. One source of error is the atmosphere. As the signal passes through layers of air, it can slow slightly. Not enough to notice directly, but enough to matter when you are measuring time with great precision. Receivers use models to estimate these delays, and the system can correct for much of it. Another source of error is reflection. Signals can bounce off buildings, water, or rock walls. This is called multipath. The receiver might hear a slightly delayed echo of the signal, mixed with the direct path. In a city street, that can make position feel a little restless. In open space, it often settles. Then there is the simple fact of weak signals. Indoors, signals may be blocked or reduced. Under dense trees, they may scatter. In a deep valley, fewer satellites may be visible. The receiver may still produce an estimate, but with less confidence. To improve accuracy, there are helping systems. Some use additional correction signals. Some use local reference stations. Some combine satellite navigation with other sensors. In a phone, you might quietly blend satellites with Wi-Fi, cell signals, and motion sensors. Not as a replacement, more like extra clues. And sometimes, accuracy is not the point. Sometimes you only need the calm certainty of general direction. A blue dot that stays near the right street. A map that helps you feel oriented. In that sense, GPS is not only a measuring tool. It is also a comfort. A quiet reassurance that the world is legible. Now, softly, we can gather the main ideas. Just the shape of them. No effort required. First, GPS begins with time. Satellites timestamp their signals. Receivers compare send time and arrival time. That travel time becomes distance. Second, satellites also provide their own position information. Your receiver needs to know where the signal came from, not only when it arrived. Third, location comes from combining distances to multiple satellites. One satellite gives a sphere. More satellites narrow the possibilities. And a fourth satellite helps correct for the receiver's imperfect clock. Fourth, the real world adds gentle errors. The atmosphere can delay signals. Buildings can reflect them. And visibility can change with the environment. And fifth, modern devices often combine satellite navigation with other quiet hints. Extra clues, blended together, to keep the estimate steady. All of it, so often, happening without you noticing. And now, we let the museum grow quieter. the exhibits remain in place. Instruments of navigation, old maps, and above them, the calm idea of satellites passing in wide arcs. Time, distance, and a soft geometry in the sky. Signals arriving, quietly, like gentle taps on the surface of the world. Nothing needs to be solved now. No coordinates. No route. Just the feeling that, somewhere above, clocks remain steady. And that steady rhythm can be borrowed by the mind. If any thoughts pass through, they can pass like satellites. Small lights. Moving on. Never demanding anything. This has been Curious Nights. GPS explained gently. And now, there is only the quiet of night. Most of the internet does not travel through space. It travels through glass. Quietly. Under the sea. Tonight on Curious Nights, we are calmly explaining how undersea cables carry signals between continents. Cables, light, repeaters, and the gentle logistics of the ocean floor. Our setting is a dim coastal cable station after hours. A quiet map on the wall. A steady hum from climate-controlled rooms. And long lines on the map that disappear into dark water. Start with a simple image. A cable leaving the shore, sliding down into deep water, and continuing for thousands of miles. It is not a thick pipeline of data. It is a carefully protected strand of optical fiber. Optical fiber is thin glass, made to guide light. Light enters at one end, and it stays inside the glass as it travels. It is held in by internal reflection, like a calm hallway for photons. That light is not just light. It is information, encoded as rapid changes in the signal. When you send a message, watch a video, or load a page, the information becomes bits. Those bits become signals. And in long-distance networks, those signals often become pulses of light. Fast, precise, and surprisingly quiet. Undersea cables look delicate in concept, so they are built with layers. Inside, the fibers. Around them, protective materials. Strength members to handle tension. And, especially near shore, heavy armoring to resist damage. Near coastlines, the sea is busy. Anchors. Fishing gear. Waves and shifting sand. So cable routes near shore are chosen carefully. And cables are often buried beneath the seabed for protection. In deeper water, things get quieter. There is less human activity. The cable can rest on the ocean floor. Dark, cold, and stable. The cable becomes part of the landscape, a thin line across the plain. One calm but important point is this. Undersea cables carry a huge share of global data between countries. They are the quiet backbone. Not glamorous, but essential. Like plumbing, but made of light. Now we step closer to the signal itself. Because the internet, at long distance, is often a conversation carried by light. In the cable station, the ocean-facing side is physical. A thick cable enters the building. But inside, the work becomes delicate. Fibers connect to equipment that can translate between electricity and light. Your devices speak electricity. Long-distance networks prefer light. To send data, the system uses a laser. Not a dramatic beam. A controlled source of light injected into glass. The data rides on that light as modulation. Tiny changes in the signal that represent the information. And it is not only one conversation at a time. Modern fiber links can carry many channels at once. Different wavelengths of light, traveling together through the same fiber. Like many quiet lanes on one dark highway. Over distance, signals fade. Light weakens. And the ocean is not a short trip. So undersea cables include repeaters. Devices placed along the route that boost the optical signal so it can keep going. Think of repeaters as quiet mile markers with a job. The signal arrives a little tired. The repeater strengthens it. And the signal continues, still made of light, still carrying meaning. When the signal reaches the other side, the process reverses. Light becomes electrical signals again. Those signals move through terrestrial networks, through cities, data centers, and local connections, until they reach the person waiting on the other end. Now we look at the journey. Because the internet does not just travel. It is routed, planned, and gently engineered around the shape of the planet. Undersea cable routes are chosen with care. They consider the seabed terrain, busy fishing areas, shipping lanes, and natural hazards. The goal is not only the shortest line. It is a reliable line. The places where cables come ashore are called landing points. Often quiet stretches of coastline with access to secure facilities. From there, the connection joins land-based fiber networks and spreads into the broader internet like roots into soil. To install a cable, companies use specialized cable-laying ships. They carry enormous lengths of cable coiled in tanks. They move slowly, patiently, paying the cable out into the water under controlled tension, like laying a thread across an entire ocean. Near shore, the ship may work with equipment that helps bury the cable. A plow-like tool can cut a shallow trench in the seabed. The cable settles in, and the sand closes over it. A quiet protection against accidents. In deep water, burial is often unnecessary. The cable simply rests on the ocean floor, pressed gently by its own weight, surrounded by darkness and time, doing its work without movement. And the network is not a single line. It is many lines, multiple cables, multiple routes, and planned redundancy. So that if one path has trouble, traffic can often flow around it, like water finding another channel. Now we speak softly about failure, not as drama, just as reality, because cables can break, and the world keeps working anyway, most of the time. Many cable faults happen in shallow water, where human activity is dense. Anchors can drag, fishing gear can snag, and storms can shift the seafloor. Near shore is the loud part of the ocean. When a cable is damaged, operators use testing to locate the fault. Then a repair ship is sent. It does not move quickly like a ferry. It moves carefully like a technician, because precision matters. At the repair site, the ship lowers equipment to the seabed. It retrieves the cable. The damaged section is removed. A new piece is spliced in, and the cable is lowered back down. A quiet surgery performed at sea. So why does the internet usually keep working? Because networks are built with alternate paths. Traffic can be rerouted across other cables and other links. Sometimes the reroute is invisible to you. Sometimes it adds delay. But the system is designed to keep flowing. Delay has a simple cause: distance. Signals move extremely fast, but the planet is large. Every extra mile adds a little time. So route choices can be a balance between safety, geography, and performance. There is a calm lesson here. The internet is not a cloud floating above you. It is infrastructure. Ships, stations, glass, and careful maintenance. And most of it is quietly out of sight. Now we can gather the story into a few calm points. Nothing to memorize. Just a gentle shape to the idea. First, much of the internet between continents travels through undersea fiber optic cables. Information becomes pulses of light moving through thin strands of glass. Second, cables are engineered in layers, especially near shore, where they may be armored and buried for protection. Third, the signal is strengthened along the way by repeaters, quiet devices that help light travel across long distances. Fourth, cable routes and landing points are carefully planned, and cable-laying ships place the lines slowly and precisely across the seafloor. And fifth, when problems happen, traffic can often reroute across other links. The internet stays resilient because it is a network, not a single path. And now, we return to the coastal station at night. The map on the wall is still. Lines crossing oceans like pencil marks. Quiet routes that never sleep. Outside, the sea looks empty. But beneath the surface, on the dark floor of the ocean, the cables rest. And through them, light keeps traveling, carrying small pieces of life from one shore to another. A message, a photo, a page loading quietly. All of it becoming signals, becoming light, becoming distance. Nothing to do now. Nothing to troubleshoot. Just the calm thought that the modern world has a hidden spine. And tonight, it is working softly in the dark. This has been Curious Nights. How the internet travels under the sea. Cables, signals, calmly explained. And now, you can let the night carry the rest of the bandwidth. You click buy. And days later, a box appears at your door. No fanfare. No visible machinery. Just smooth arrival. But behind that smoothness is one of the quiet miracles of modern engineering. A plain steel rectangle, built to the same rules almost everywhere on Earth. The shipping container. Tonight on Curious Nights, the quiet engineering of shipping containers. How goods move so smoothly. Our setting is a port at night. Floodlights on steel. Slow cranes. And stacks of identical boxes that look ordinary. Until you realize how much they quietly coordinate. A shipping container is not just storage. It is a standardized interface. A shared physical language that ports, ships, trains, trucks, and warehouses all understand. Before containers, cargo often moved as many separate items. Crates, bags, barrels. Each handled again and again. More labor. More damage. More waiting. The container changes the unit of movement. You stop moving the contents. And you move the whole sealed box instead. One lift, one lock, one transfer. Repeat, calmly, thousands of times. Most containers are built around common global sizes. You may hear 20-foot units and 40-foot units. Not because those numbers are magical, but because standard dimensions let equipment be reused everywhere. And the container is designed for a rough life. Salt air, rain, sun, forklifts and cranes, ocean vibration, stacking pressure, and long waits in open yards. So even though it looks simple, it is built with a very specific job. To protect goods, to be lifted quickly, to lock reliably, and to fit into a global rhythm without needing custom handling at every border. If you look closely at a container, the most important parts are the corners. Those reinforced corner castings are the universal handshake. They are where cranes lift, where containers stack, and where they lock together. The locks are called twist locks. Simple hardware that turns and holds. One small rotation that says, this container is now part of a larger structure. Truck to yard. Yard to ship. Ship to rail. Rail to distribution center. This is what engineers love. A clean interface. Not flashy. Just dependable. It allows different machines, built by different companies, in different decades, in different countries, to cooperate without negotiation. Standardization also simplifies planning. A ship can be designed around container stacks. A port can be designed around predictable lifts. A rail terminal can be designed around predictable clearances. Even warehouse shelving and door heights become calmer decisions when the incoming unit is consistent. And consistency creates speed without rushing. When every container fits, the whole system spends less time improvising, less measuring, less repacking, less human friction, more smooth motion. At sea, containers are stacked like quiet buildings. And that means structure matters. The container's frame carries much of the load. The corners are designed to take compression from the stacks above. So weight travels down through corner posts, rather than crushing the walls like a cardboard box. You may notice the walls are corrugated. Those repeating ridges are not decoration. They add stiffness without adding too much weight. Like folding a sheet to make it harder to bend. A simple geometry trick that shows up across engineering. The doors are another careful compromise. They need to seal well. They need to resist prying and weather. And they need to open after weeks of vibration, salt, and temperature swings. So the locking bars are simple, strong, and repetitive on purpose. Inside, the floor is built for abuse. Pallet sliding. Forklift tires turning. Concentrated loads. The container is a machine for being handled. And being handled again. Even the small labels matter. Weight limits. Identification numbers. Safety markings. Because a global system runs on clear constraints. A calm yes and no that keeps motion safe. Now we watch the system at work. A container ship arriving. And a port turning it around with quiet precision. From a distance, cranes look slow. But the efficiency comes from predictability. Spreaders connect to the corner castings. Twist locks engage. And the container rises as one stable unit. Then the container moves into the yard. And the yard is not just storage. It is a buffer. a place where timing differences are absorbed. Ships arrive in waves. Trucks arrive in streams. Rail moves in scheduled blocks. The yard makes those rhythms compatible. Containers are stacked, sorted, and retrieved with planning in mind. Some need to leave first. Some require inspection. Some contain time-sensitive goods. The goal is to minimize unnecessary reshuffling. Because every extra move is time, energy, and risk. From there, the container becomes intermodal. Same box. Different vehicle. A truck chassis for a highway run. A railway car for a long inland stretch. Another truck for the last miles. The container stays closed. The goods stay protected. Not every container is the same. Some are built for temperature. Some for liquids. Some for heavy machinery. But they still follow the same basic logic. Standard handling, predictable movement. Refrigerated containers are often called reefers. They are insulated boxes with built-in cooling systems. And they need power along the journey. At ports, in yards, and on ships, they plug into electrical points. A quiet detail that protects entire supply chains of food and medicine. Other containers are specialized too. Tank containers for liquids. Flat racks for oversized cargo. Open tops for loads that need a crane from above. Different shapes. Same global handling habits. And then there is security. Most containers travel sealed. The seal is often simple, but it provides accountability. If the seal is intact, the box has remained closed in transit, and the system can trust its own process. The modern magic is that this trust scales. Millions of containers, thousands of ports, countless handoffs. And still, most of the time, the box arrives where it should. Because the engineering is quiet. And the rules are shared. Now we can gather the story into a few calm points. Just enough to keep. Not enough to effort. Shipping containers work because they are standardized. One predictable unit that ships, ports, trucks, and trains can all handle the same way. The corners matter most. Corner castings and twist locks make lifting and stacking fast, strong, and repeatable. The structure is simple, but intentional. Frames carry stacked loads, corrugation adds stiffness, and doors and floors are built for constant handling. Ports run like choreography. Yards buffer timing. And intermodal moves let the same sealed box travel across ocean, rail, and road. And now, we return to the port at night. Stacks of containers sit quietly under tall lights. Each one a small promise that something will arrive somewhere else without needing you to think about how. A crane moves with measured patience. Metal meets metal. A twist lock turns. And the box lifts, steady and balanced. It is not loud engineering. It is quiet engineering. Rules that fit together. Hardware that repeats. And a world that moves smoothly, one sealed rectangle at a time. This has been Curious Nights. The quiet engineering of shipping containers. How goods move so smoothly. And now, you can let the night handle the logistics. Welcome. Settle in, as if you've stepped into a quiet kitchen after hours. When the day has finished speaking. Tonight, we'll follow a calm, unhurried story. The science of coffee, from bin to brew. There's nothing to solve. Nothing to remember perfectly. Just a gentle sequence of small, practical ideas. Arranged like a tidy row of cups. We'll move slowly through 4 simple chapters. Where coffee begins. How the beans are prepared. What roasting changes. And how grinding and brewing shape what you taste. If you drift off partway through, that's completely fine. The story will keep its calm pace. And you can rejoin it wherever you happen to be. Now, very gently, let's begin at the beginning. Coffee begins as a plant. Not as a flavor. Not as a habit. Not as a morning ritual. Just a living thing. Growing patiently in places with the right balance of warmth, rain, and shade. If you ever see a coffee plant, the first surprise is how ordinary it looks. Glossy green leaves. Small white blossoms. They can smell faintly like jasmine. And then, the fruit. Because a coffee bin is not a bin in the botanical sense. It's a seed. And it lives inside a fruit often called a coffee cherry. Imagine that cherry for a moment. Usually red when ripe. Sometimes yellow, depending on the variety. Inside, there's sweet pulp. And within that, typically 2 seeds pressed face to face. Those seeds are what become the coffee you recognize. 2 names come up often in coffee. Arabica and Robusta. It's easiest to treat them as 2 broad families, each with its own tendencies. Arabica is often described as more delicate in flavor, with a wider range of aromas. Robusta is often described as sturdier, with a bolder, more direct character. Those are only generalities, of course. But they help as a first map. From a science point of view, what matters is that flavor begins long before roasting. The variety of the plant, the soil and rainfall, the altitude and temperature. All of these shape what the seed stores as it grows. It's a slow accumulation. Like a library being stocked one quiet book at a time. There's also a calm practicality to coffee farming that's easy to miss. Coffee doesn't ripen all at once. On the same branch, you might find unripe cherries, ripe cherries, and flowers preparing for the next cycle. So harvesting is often selective, done in passes, with attention and patience. Not a single dramatic moment, but a repeated, careful routine. And then, once those ripe cherries are gathered, the next question arrives quietly. How do you turn a fruit into a stable seed? Something you can store, ship, roast, and brew. That's where processing begins. Coffee processing is, in a simple sense, the art of removing layers. First the skin and fruit, then the sticky, sugary layer beneath, until you are left with the seed, clean enough to dry, and stable enough to keep. Two common approaches are often described as washed and natural. In a washed process, the fruit is removed fairly soon after harvest. The seeds are then soaked or held in water, so the remaining sticky layer loosens and can be rinsed away. In a natural process, the cherries are dried more like fruit would dry in the sun, with the seeds still inside for much of that time. Even without going into technical detail, you can sense the difference. Washed processing often creates flavors people describe as clearer, cleaner, more directly tied to the bean itself. Natural processing often creates flavors people describe as fruitier, rounder, sometimes a little wilder. Not better or worse, just different paths through the same landscape. There's a quiet bit of biology here, too. Because whenever fruit and sugars are present, tiny organisms are interested. Yeasts and bacteria exist on surfaces all around us, and they can begin to break down sugars. This is fermentation in its simplest sense. A slow transformation, guided by time, temperature, and environment. In coffee, fermentation is not usually the headline. It's more like a gentle supporting character. It can help remove that sticky layer, and it can subtly shape flavor by changing what remains on the seed and how the seed surface develops. It's a reminder that coffee is not just an industrial product. It's a biological material that has been carefully handled. After processing comes drying. And drying is about calm stability. Too much moisture, and the beans won't store well. Too little, too quickly, and the beans can become brittle and uneven. So producers aim for a steady approach, turning and resting the beans as they slowly reach the right balance. At this stage, the beans are called green coffee. They look pale, slightly bluish green, and they smell faintly grassy, or a little like dried peas. It's not the aroma most people think of as coffee yet. That familiar scent arrives later, with heat, and the calm, transformative work of roasting. Roasting is where coffee becomes aromatic. It's the point in the story where a quiet, stable seed begins to release something more expressive. And it happens for one simple reason. Heat encourages change. Imagine a small roastery at night. The gentle rotation of a drum. The soft, dry sound of beans tumbling against metal. Roasting is carefully managed warmth, applied over time, so that the bean changes from the outside in. A lot of flavor development can be understood as a few calm ideas. One is that water inside the bean turns to steam and expands. That expansion alters the bean's structure, creating tiny pockets and pathways. Another is browning, the same family of changes that makes toast smell comforting and gives roasted nuts their warmth. These reactions create new aroma compounds, as if a cupboard has been opened after a long time. People often talk about roast levels: light, medium, dark. It can help to think of roast level as a question. How far is the transformation taken? A lighter roast often keeps more of the bean's original character, including brighter, fruit-like notes. A darker roast often leans into deeper, toastier, more caramel-like flavors. And in between, there are many calm choices, each with its own balance. Roasting is also a story of timing. Not in a stressful way, in a craft way. Roasters pay attention to how quickly the bean warms, how evenly it changes, and how the scent shifts as the roast develops. It is patient observation, repeated day after day, until the senses learn the pattern. Once roasted, the beans need a little time to rest. They release gases gradually, and their aroma settles into a more stable form. And then, when you're ready to brew, the next calm choice appears: how finely to grind. Because grinding controls how water meets coffee, and how flavor is gently carried into a cup. Grinding is a quiet kind of geometry. When you grind coffee, you increase its surface area. And surface area is simply the amount of coffee that water can touch. A calm way to picture it is to imagine stones on a shore. Large pebbles have less total surface area than the same amount of stone crushed into sand. Water can move around sand differently, reaching more tiny edges and corners. Coffee works in a similar way. Finer grinds allow water to meet more coffee more quickly. Coarser grinds slow that meeting down. Now, brewing. Brewing is often described with the word extraction. It sounds technical, but the idea is gentle. Water moves through coffee and carries certain soluble compounds with it. Some compounds dissolve readily, arriving early in the brew. Others take more time, arriving later. This is why time matters. This is why grind size matters. And this is why water temperature can matter, too. But none of it needs to become a project. You can think of these variables as quiet dials on an old radio. A slight turn changes the sound. And then you simply listen. Different brewing methods are different ways of arranging contact between water and coffee. Some methods let water pass through quickly. Others steep coffee and water together, like a slow conversation. Some use paper filters that catch oils and fine particles, creating a cup that feels lighter and clearer. Others use metal filters that allow more oils through, creating a cup that feels fuller. And then there is aroma, which is half the experience. Much of what we call taste is actually smell, carried upward as warm vapor. That's why coffee can feel comforting even before the first sip. It arrives first as a scent, and only then as a flavor. If you ever prefer coffee without caffeine, the same story still holds. The bean is still grown, processed, and roasted with care. The cup can still carry aroma, texture, and warmth. And now, with the story in place, we can let it soften into a calm recap. Let's gather the main ideas gently, as if we're putting things back on the shelf. Nothing new, just the calm shape of what we've already seen. Coffee begins as a plant, a glossy-leaved tree that grows cherries. And inside each cherry are the seeds that we call beans. Plant, cherry, seed. Then comes processing. Removing the fruit, washing or drying. Letting time and careful handling guide the bin towards stability. Processing is the quiet work of preparing something natural for travel and storage. Then roasting. Warmth, steadily applied. Changing structure. Deepening color. And creating aroma. Roasting is where coffee becomes recognizably coffee, especially in the air. Then grinding. Changing surface area. Changing how quickly water can meet the coffee. And finally, brewing. Water and time. Carrying soluble flavors into a cup. Plant. Processing. Roasting. Grinding. Brewing. A calm sequence. And if you like, you can let that sequence fade into the background now. Like a familiar clock ticking gently in another room. Now we can slow down even more. There's nothing else you need from this story tonight. It can simply be a quiet soundtrack while you rest. You might picture that calm kitchen again. The lights low. The air still. And on a counter, a small bowl of beans. Waiting patiently, as they always do. Coffee begins as a plant, a cherry, a seed. Then, quietly, the careful steps: processing, roasting, grinding, brewing. And you don't have to hold any of it in mind. You can let the details loosen. Let the story become softer and softer. Just a gentle sequence, like footsteps fading down a quiet corridor. If you notice your thoughts wandering, that's all right. You can return to one simple idea: warmth, time, and a calm breath arriving on its own. Good night. Tonight, we take a slower journey. Not just through history, but into the inner workings of machines that are learning to drive themselves. Because behind the idea of autonomy, there is something more intricate. Not magic, not instinct, but layers of sensing, prediction, and decision. To understand it, we begin with a simple question. What does a self-driving car actually need in order to drive? The answer unfolds in stages. First, it must see. Then, it must understand. And finally, it must decide. We begin with perception, the ability of the vehicle to observe its surroundings. Most modern autonomous systems rely on three primary types of sensors. Cameras, which capture visual detail. They recognize lane markings, traffic lights, and the subtle gestures of pedestrians. Radar, which measures distance and velocity. It performs reliably in rain, fog, and darkness. And LiDAR, which emits pulses of laser light. Each reflection returns with a timestamp, allowing the system to calculate depth with high precision. Together, these sensors produce overlapping views of the world. This process is known as sensor fusion. Instead of trusting a single input, the system combines them, reducing uncertainty and increasing reliability. The result is a continuously updated model of the environment. A digital reconstruction of roads, vehicles, and movement. Seeing the world is not enough. The vehicle must also know where it is. This is the problem of localization. GPS provides a rough position, but it is not precise enough for driving. Errors of even 1 meter can place a car in the wrong lane. So autonomous systems rely on high-definition maps. These maps contain far more detail than consumer navigation systems. They include lane geometry, curb positions, traffic signal locations, and even the slope of the road. The vehicle compares its sensor data to this map in real time, matching features like landmarks and edges. This process, often using techniques such as SLAM, allows the car to position itself with centimeter-level accuracy. Once the world is perceived and located, the system must anticipate what happens next. This is the prediction layer. Each object is tracked over time. Its velocity, direction, and intent are estimated. A pedestrian near a crossing may step forward. A cyclist may change lanes. These are not certainties. They are probabilities. On top of this, the planning system generates possible paths. Each path is evaluated for safety, efficiency, and comfort. The chosen trajectory is then passed to control systems, which convert it into steering, braking, and acceleration. This entire cycle repeats many times per second, creating the illusion of smooth, continuous driving. At the center of these systems lies machine learning. Neural networks process visual data, identifying objects, segmenting scenes, and recognizing patterns. These models are trained on vast datasets. Millions of miles of driving, across cities, weather conditions, and edge cases. More recent systems integrate vision, language, and action, allowing them to reason about complex scenarios. But despite this sophistication, the system does not understand the world as humans do. It approximates it through data, probability, and continuous adjustment. And so, autonomy is not a single breakthrough. It is a layered system. Sensing, mapping, predicting, deciding. Each layer quietly supporting the next, until motion appears effortless. And tonight, as you rest, these systems continue learning, processing roads, refining decisions, moving, step by step, towards something quieter. A world where motion becomes effortless. Good night. Every moment of our lives unfolds in time. We wake in the morning. We move through the day. And slowly, almost without noticing, the hours pass. Time feels familiar, almost ordinary. And yet, when we pause to think about it carefully, something unusual appears. Time always seems to move in one direction. Forward. Never backward. A broken glass does not reassemble itself. Smoke does not return neatly to the candle. The past remains fixed behind us. This direction is often called the arrow of time. A steady movement from past to future. But physics presents an interesting puzzle. Many of the fundamental laws of nature do not actually prefer a direction. If the equations were reversed, they would still work. The mathematics itself does not distinguish between forward and backward. So why does time appear to move forward? Why does the past feel fixed while the future remains open? To explore this question, we need to look at several ideas. Entropy, relativity, the clocks we use to measure time, and the way our own minds perceive the passage of moments. Together, these ideas reveal something quiet and fascinating. Time may not be quite what it seems. To understand why time appears to move forward, we begin with a concept from thermodynamics. This concept is called entropy. Entropy is often described as a measure of disorder. But a more careful description is the number of possible arrangements a system can have. Consider a simple example. A neat stack of papers sitting on a desk. The arrangement is orderly, very specific. Now imagine those papers scattered across the floor. There are many more ways for them to be messy than to be perfectly stacked. Because of this, natural processes tend to move toward higher entropy, from ordered arrangements to more probable ones. This gradual increase in entropy gives time a direction, a statistical push from order toward disorder. And this is why certain events feel irreversible, because reversing them would require an extraordinarily unlikely rearrangement of particles. In everyday life, time feels steady and universal. 1 second passes for everyone, everywhere. But modern physics tells a different story. According to Einstein's theory of relativity, time is not perfectly constant. The rate at which time passes can depend on motion and on gravity. Clocks moving at very high speeds tick slightly more slowly. Clocks closer to strong gravitational fields also run more slowly. These effects are small in everyday situations, but they are measurable, and they are real. Time, it turns out, is connected to space. Together they form something called spacetime. Humans have always searched for ways to measure time. Early civilizations watched the movement of the sun, the slow arc of shadows across the ground. Later came mechanical clocks, carefully engineered gears and pendulums. Today the most precise clocks are atomic clocks. They measure time using the vibrations of atoms. These clocks are so accurate that they would lose less than a second over millions of years. And yet even these clocks reveal something interesting. Time itself can vary depending on location and motion. The arrow of time describes the direction from past to future. This direction is deeply connected to entropy. As entropy increases, time appears to move forward. In principle, the microscopic laws of physics do not forbid time moving backward. But the probability of all particles spontaneously reversing their paths is unimaginably small. So in practice, the arrow of time always points in one direction. There is one final layer to the story of time: the way our minds experience it. Psychologists have found that time perception is not constant. Moments of excitement often feel brief, while moments of waiting can feel long. The brain constructs a sense of time from memory and attention. In this sense, time is not only a physical phenomenon, it is also a psychological one. To understand the arrow of time more deeply, scientists often look toward the beginning of the universe. Observations suggest that the early universe was in an unusually low entropy state, a condition of remarkable order. Matter was distributed smoothly across space. Energy was dense and uniform. Over billions of years, gravity gradually shaped this smooth beginning into stars, galaxies, and planets. Structures formed. Complexity increased. But overall entropy continued to rise. This ancient starting point may explain why time appears to move forward. The universe began in an ordered state and has been evolving toward greater disorder ever since. Gravity also plays a subtle role in shaping our experience of time. According to general relativity, gravity is not simply a force. It is a curvature of space-time itself. Massive objects bend the fabric of space-time around them. And within this curved geometry, time flows differently. Clocks closer to massive objects tick more slowly. This effect is small on Earth. But near a black hole, time dilation becomes extreme. From a distance, an object approaching the edge of a black hole would appear to slow dramatically, almost as if time itself was stretching. While relativity reshaped our understanding of time at cosmic scales, quantum physics raises new questions at the smallest scales. In many quantum equations, time appears as a simple parameter, not always as a dynamic part of the system. This has led physicists to ask an unusual question. Could time itself be an emergent phenomenon? Something that arises from deeper physical processes rather than existing as a fundamental ingredient. If this idea is correct, time may not be a basic component of reality, but a pattern that emerges from more fundamental relationships. Some interpretations of relativity suggest a striking possibility. The past, present, and future may all exist together within space-time. This concept is sometimes called the block universe. In this view, time does not flow. Instead, all moments exist as part of a four-dimensional structure. The sense of moving from past to future may arise from the way consciousness experiences events. Like reading a story one page at a time. Even though the entire book already exists. One of the deepest puzzles in physics is that many fundamental equations work equally well forward and backward in time. If a video of particle motion were reversed, the equations describing it would still remain valid. This symmetry suggests that the laws themselves do not prefer a direction. Instead, the direction of time may arise from statistical conditions in the universe. From probability rather than from fundamental law. Another clue about the direction of time comes from memory. We remember the past, but we do not remember the future. This asymmetry is deeply connected to entropy. Forming memories requires physical changes in the brain, and those changes increase entropy. In other words, remembering events is itself part of the forward movement of time. Despite the complexity of physics, our daily experience of time remains simple. We measure it with clocks, organize it with calendars, and structure our lives around its steady passage. Seconds become minutes. Minutes become hours. And gradually those hours become memories. Time is both a scientific concept and a deeply personal experience. The quiet science of time reveals something remarkable. What feels like a simple flow may actually arise from deep physical processes. Entropy shaping the direction of change. Relativity bending the passage of seconds. And the human mind interpreting those moments as experience. Time moves forward for us. Moment by moment. Memory by memory. And within that steady movement, the story of the universe quietly unfolds.